ambient space that fixes that point also leads to variance per sphere. So it's maximally symmetric, which you would expect to happen if you have neatness. Okay. All right. So where does this theorem come from? First, tell you what motivates this theorem. Where does the proof come from? Where the ideas come from? Certainly, the main idea goes back to Hahn idea. He proved that in R3, the simple setting, round spheres are the only constant curvature spheres, and then there's just certainly one of the congruence for every radius of the sphere. Okay. Then you have a sort of really nice improvement on that work of Hahn back in probably earlier than that. But anyway, 2004, probably the journal article. If you have a four-dimensional symmetry group, then you might expect your spheres to fit up like a Shang. If you have a four-dimensional symmetry group, you might expect that your sphere is a surface of revolution. So if the ambient space has lots of symmetry, then maybe your sphere also has a symmetry. And then you can somehow describe these spheres by some curve, says like some ODEs. So anyway, that's what happens. And from that complication of ODEs and what the curves are, you can prove that they are uniquely defined by their curvature. Okay, so that's sort of key thing. Then we sort of go forward quite a few years. Probably this is around 2010 when we figured out these things, but it took a while for these various papers to get accepted. A big sort of leap forward was an example where we study Sol. So Sol is a Lie group, and it has a left-and-right metric. And here's sort of the first in view of what that metric is. It turns out there are lots of other metrics. This is not the only left-and-right metric on Sol. And so even though we proved this theorem of uniqueness and some nice results about spheres in here, we didn't know this theorem for other left-and-right metrics. There are other left-and-right metrics on Sol, left-and-metric ones, and for those we didn't know the theorem. So what is this theorem? You take this particular metric on R3, then you know that the spheres are unique, embedded, and have index 1. Furthermore, if you're willing to translate them to their center of mass or center of symmetries at the origin, then they have all these other symmetries. Vertical planes of symmetry, they have two vertical planes, x, y, xz, and a y-z plane for plane symmetry of that metric, and you also have some diagonal lines and ones that you can rotate by 180 degrees. So you have, and those are how the ambient symmetries. Okay, and so they tell me about here, they had proved a substantial result, but they couldn't prove it for all being curvatures. For all being curvatures, one needed to get what's called area estimates. One needed to prove that Sol has secret constant 0. Sol has is a unimodular metric group, so it's secret constant is 0 anyway. So it's 0, and what they knew is that the mean curvature was reasonably big, then they would result. But as the mean curvature got closer to 0, you have problems of knowing if you have area estimates. All the spheres got mean curvature with area with mean curvature bigger than a half. Do you have a bound on their areas? So there's these kinds of questions, and like I was going to say, figure out those area estimates. So as long as I can away from the zero constant, away from 0, I can find these estimates, and therefore complete their argument to all mean curvatures. And that's kind of the hard part of these area estimates of this other theorem. So here's a rephrasing of that theorem. Okay, so this is I'm just going to think of a connected case. Okay, three-dimensional homogeneous. I'm not going to look at this case. This case, think of it four-dimensional symmetry group, completely understood. You can explicitly write down all the constant curvature spheres. We're not looking at this case. That means we're looking at the case where X has a Lie group structure. And I'm going to use that really strongly in the proof. That group structure plays a very important role in understanding the proof of this theorem. Makes it very clear to the money. So what's the situation? We're taking work at S3, that's a three-dimensional family metric sphere, and for each metric, you have a constant mean curvature sphere for any value of the growth number. If you're taking work to R3, notice how you replace secret constant by the critical mean curvature. That's one of the more natural number to look at in this problem. And in the case of S3, you also know that you have a uniform bound on the areas. So if you look at all kinds of mean curvature spheres and you choose a left-and-right metric, then there's a uniform bound. There's a sphere which is biggest. It's not always the middle one. In fact, it's not the middle one. So and the other key property is the sort of bounding tape all the convex size, index 1 and LC3. Okay, so like I say, we're really looking at this theorem in a setting where X has a Lie group structure. Okay, now you might have one parameter family of Lie group structures. So I'm going to pick ahead of time for the group. I'm going to pick one of these Lie group structures. Okay, and I'm going to fix it. For example, X1 space has lots of Lie group structures, so it's I'll have a my example is a left-and-right metric, but a whole one parameter family of different Lie groups. So we're going to fix that Lie group structure, and that comes back to my first picture. Remember, we have the Gauss map. We can take a normal vector, unit normal on the surface. We can left translate it to the origin in our space, the density element, just remember the role of our origin, and it gives me a point in a unit sphere at the tangent space of the density element. Okay, that's going to be my Gauss map. Okay, and that's called the left-and-right Gauss map. And I'll just say a couple of things about it. A real key result is that we can completely characterize constant mean curvature surfaces in terms of a wire thrust representation and its Gauss map. So if you have some kind of a disk in the plane, and you're looking at mass into the two-sphere, and you can very rapidly project it onto the complex plane, say from the south pole, then it turns out that to be a constant mean curvature surface, this means it satisfies some formal second-order PDE. Okay, and so concepts are like necessary and sufficient conditions, and furthermore, you get this map into the Lie group, and it's well-defined up the level translation. So there are some minor restrictions of certain values of mean curvature, and the image of the Gauss map. But anyway, most of the time this is basically what I talk about. It's a wire thrust representation. It's defined up the left translation. Okay, so how does this proof work? It's a moduli space argument. Okay, so we're gonna create a moduli space, and remember, the theorem says there's one surface for every mean curvature. So I'm gonna make my moduli space match up with it. I'm gonna say a curve, and I start with something I understand better. Sigma is a fixed echelon surface in X of index 1. Okay, so fix this, for example, take a teeny volume, solve like a parametric problem. You can see you have a little sphere, a little teeny, almost round sphere, and that little almost round sphere has at least one. Okay, so you think this, there's at least one, but I'm gonna fix it for a while. I'm gonna fix it for a while before I look at any kind of other spheres. We'll fix this one at index 1. Okay, so the first thing you note is stability opposite Schrödinger operator on the surface, and it has at most nullity 3. In fact, it has exactly nullity 3 because I can move the sphere around. There's no non-zero vector field anyway. So I have nullity exactly 3. Okay, you can't have bigger than 3. That's going to help us during a deformation process. So I values can't cross 0 somehow. The ones that are from the wide various vector fields on the group. So just help them understand things. This is, so I'm going to work with this modulate. Non-congruent index-1 spheres. Okay, so remember index-1, I'm looking at all spheres, looking at these. The next I would analyze one-dimensional manifold. So if I take a given sphere, if it's index-1 null degree, I can find this in terms of the curve of certain spheres nearby it that have changing in curvature. So my Kramer family, I can find my one manifold. It's pretty easy to do because the nullity is free, you can show all the motions. You can get rid of some non-existing non-degenerate. Okay, so that's the function. That's pretty straightforward. The next thing is surprisingly tricky to do. It says you now look at this less invariant Gauss bound. Okay, so you have your sphere index-1, you have a map of the two-sphere, and it's a different margin. So that sounds kind of interesting with our grading, right? You got grading the now, kind of like grading spheres. Anyway, and this is like I said, sometimes surprisingly tricky. If you ask me to write down the proof of this, I would have trouble. I would have to go back to the paper and kind of look it up. But anyway, it's a nodal, that is kind of reasonable, and it uses a nodal domain argument, something in the kernel derivative map. Basically, it's a sufficient to show the local dimorphism, right? It's connected. So, and then you use that representation theorem I was talking about before to get some kind of contact with some other surface and things. But that's step 2. And once you have step 1, step 2, you immediately get curvature estimates. Because when you rescale the points of big curvature, I say curvature estimates as long as the mean curvature is bounded from above. Right? Certainly there's no curvature estimates of the whole each-ground sphere. So think of bounding the mean curvature from above, you have curvature estimate. And that's easy to see because when you're rescaling, produce minimal surfaces in R3, they're not flat. So what's the degree of their Gauss bound? Negative degree, or negative Gaussian curvature. So that's just kind of trivial to get curvature estimates. Okay, this is the really hard part of the theorem, and I'm going to accommodate that. I'm going to be able to do it. Give you a pretty good idea of how that works in the 3-sphere. So there are 2 kinds of area estimates. That's an area estimate. Well, this is the easiest case. If the topology of the 3-sphere, or the group is SU2, then you just have a local estimate. Areas of all spheres are boundable. It's not the biggest value if you want to get more sense. Okay, so that's what we understand what that means. What's not so clear is what it means when you're not SU2. So at night, SU2 means topologically R3. And think about what happens in R3, because it's flat metric. What happens to the area of spheres? Well, they go to infinity. As the mean curvature goes to 0, which is 1 over the radius of the sphere, then you have this property that you don't get area estimates. But as long as I'm willing to back away by any amount from the critical mean curvature, and any positive amount, then I have area estimates. It's only when I approach this critical mean curvature that the area goes to infinity. And that's what happens. The area always goes to infinity, but you need this estimate to try to do compactness arguments to try to understand what the scaling is. So once I have that, just one more thing. That previous theorem I talked about showing the critical mean curvature is half the integer constant. That theorem already not hard to see that there are no spheres with critical mean curvature when you're topology R3 and stuff. So that's if you went back and saw that, it's really easy to understand. Okay, so step 5. So once we have curvature estimates and we have area estimates, then we can understand this whole family. You have the original surface sigma, it's in a one-dimensional family, and because we have it's not hard to see that. In fact, this whole space, this whole 0. I'm thinking if I go to negative mean curvature, then I'm just going to block it off. So this is joint work with Alim Ghulam from Maryland and Professor Yao. So we have put 2 papers on peptide recency with the title in the title recency and the surface scheme. One of them we developed a twofold theory. These moduli spaces which I will define in my talk about algebraic surfaces, and the other one we connected them to stable geometry. And my talk today is a summary of these 2 different papers. We also earlier, before these 2, we put up some paper on archive in collaboration with Sergei Bukov, Professor Liu, and Professor Yao, which we actually originally studied this problem using gauge theory and gauge reductions related to the triple geometry, the triple geometry. Okay. So let me give you somewhat background on surface schemes. These are algebraic spaces which were first constructed by Alexander Grothendieck. He was interested in parameterizing closed subschemes of objective space. And he constructed this Cook scheme in string 4, and his schemes are particular special case of Cook schemes. After that, his schemes became such fundamental ingredients in modern algebraic geometry. Many people worked on them, and especially his first points on surfaces and threefolds became somehow focused on the attention of many mathematicians and physicists. And as you will see today, these are related to physics as well. Okay, so many people, more contemporary mathematicians, worked on these. I just show you kind of a pictorial history. So this is Ravi Hartshorn, who studied connectedness of different schemes of curves, for example. This is a picture of Nitin Nitzur. He also worked on constructional aspects of different schemes and Cook schemes and so on. This is a picture of John Xavier. He studied combinatorics of these implicit schemes. This one, some of these pictures actually, they will come up later in my talk. This is a picture of Manfred Len, and he studied cohomology of implicit schemes. This is one of my favorites, Ludwig Goethe. He calculated Decky numbers of different schemes of points on algebraic surfaces, and he constructed generating series of these numbers, and he proved modularity properties of these spaces. Of course, Richard Thomas, in the context of Dowson-Thomas theory, he studied intersection numbers of modular sheaves, and this was something, some new field he introduced in order to kind of answer certain questions about Rama-Witten theory. So if you ask your sheaves to be ideal sheaves of subspaces of some threefold that they curve, your modular space is indeed different from a curve on a threefold. So he studied different schemes too, and Javier Bukov, who did plenty of work on different schemes of surfaces and threefolds, using algebraic geometry and representation theory. This is of course a picture of Rahul Pandey, who also did plenty of work on this and many results, and he also collaborated with Andre and Richard Thomas, and of course, something I just mentioned, Professor Dowson. Okay, so this is there are many others which I just mention a few here as an example. So let's discuss some background. Let S be a non-singular projective surface over complex numbers. So 2 complex dimensional smooth manifolds. One of the objects we're going to study is the infinitesimal point. So for any non-negative integers, the infinitesimal points of the moduli space are parameterizing things like this. So configurations of points on the algebraic surface. And in order to parameterize these, you need to kind of give the total sum of how many points you have, and you need to count points with their team theoretic multiplicity. So the total sum of multiplicities is what we call length. You fix the integer and there's a moduli space that parameterizes these, and that's the infinitesimal point. This is a notation for it. Next one is inverse scheme of divisors in the algebraic surface. These are like naked curves, if you like. These are divisors, and to parameterize them, you need to fix their cohomology class. You take some elements of second cohomology of the surface with integral coefficients such that the onus is effective and the difference from a curve transforms into divided with that class. The next object of the study is kind of decorated with points and curves. So if you like, this is a moduli with inhibits from a curve on points. Algebraic geometer, instead of saying curves on points, calls them non-pure one-dimensional subspace. Pure one-dimensional subspace means just a divisor. Non-pure means it could be a divisor together with a zero-dimensional subspace attached to it. And of course for this, we need to fix the number of points which is tan and the cohomology class of the divisor. So that's the notation. Okay, and somehow, in order to transform these, you can, in algebraic geometry, transform these, it's often calculated to look at G. You can look at functions vanishing on this configuration of points and curves, see the modules over the local coordinate string of this interior surface, and they make an ideal. It's called an ideal sheet. And the second first class of the ideal sheet gives you the number of points, and then this divisor has the class data, and I call this whole configuration Z prime zero-dimensional piece plus the divisor. So this is our notation. Now some remarks about these interfaces. The inverse from a point, if the surface is smooth, the inverse from a point itself is smooth. So it's the smooth variety of dimension, complex dimensions to n. Okay? The inverse from a curve, however, if you like naked surface, or the inverse from a divisor, is in general not unless for any line bundle on that algebraic surface, whose first chain class is equal to our given fixed cohomology class, you have the vanishing condition that the cohomology is bigger than equal to 1 of that line bundle vanish for every line bundle. The first chain class given by data. Okay. And the third result, which is also kind of could be seen easily, is that the inverse from a curve of point is given as a product, as multiple product of inverse from a point and inverse from a divisor. So this you can see in different ways. If you look at functions vanishing on a sum of union of points and curves, you can write a tensor product of functions vanishing on points, those are ideal points, and functions vanishing on divisors, and that's a line bundle, which is one transcribed. Okay, so these are the results. Now my talk is about nested inverse schemes, so maybe I should tell you what the nested subscheme means. Again, it starts with this algebraic surface, and this time you're interested in nested configurations of points and curves. So I have union of a curve, make a curve or a bunch of curves and some zero-dimensional subschemes, I call them Z prime 1, and I have another configuration, Z prime 2, and I would like them to fit inside each other as subschemes, and the whole thing has a subscheme of the algebraic surface. So how do we algebraically transcribe these? So the same way that for inverse scheme of points or curves, ideal sheet for these algebraic objects, it should give you a way of transcribing the nested inverse schemes could also transcribe by taking advantage of nested ideal sheets. So what does that mean? Of course, this video we see that you can forget about Z prime 2, and look at functions vanishing on this configuration of points and curves, that's an ideal sheet. You can forget about Z prime 1, and look at functions vanishing on Z prime 2, that's an ideal sheet. And the fact that Z prime 2 fits inside Z prime 1 tells you that the ideal sheet of Z prime 1, but these are functions vanishing on it, fits inside ideal sheet of Z prime 2. And that gives you an injective map C, C1 in my notation. Okay. There's another way of writing this too, which I could use this third property in here that the inverse scheme of the product of the inverse points and curves. So each one of these one-dimensional non-pure subschemes has zero-dimensional pieces. So I call one of them Z1 with length N1, Z2 with length N2. Then, of course, they have the dividable parts as well. I call the union of those divided D1 and D2. And it's just the fact that, as I mentioned, the sheaf of functions vanishing on this union, Z prime 1, Z1, union D1, can be written as a tensor product of ideal sheaf of functions vanishing on points times the functions vanishing on the D1, and that's a line bundle. So it's an ideal sheaf, but because it's a divisor, it's also a line bundle. And same in here, I can rely I of D prime 2 and I of D2, the zero-dimensional piece times the line bundle. And so this map is still an injective map between the two. Now the reason you're doing that is because now this guy being a line bundle is an invertible sheet, and I can move it over here. So let's do that. So now I can simplify, and this injective map C1 this time can be written as ideal sheaf of points with an injective map into ideal sheaf of points on D2 times some line bundle, which sees the difference of these two divides. And of course I can forget about D1 and D2, and I can find some curve, so I can class is equal to D1 minus D2, and basically just use that to transcribe. So how many pieces of data I need? I need the length of D1, and I need the length of D2, so N1 and N2, and I need an effective curve class for C1, so and a map, an injective map to transcribe this two-fold nesting of one-dimensional subspace. Okay? Alright. So in general, I can increase the length of nestings, I can look at the threefold nestings, I can look at the r-fold nestings, and the theory I'm talking about today is for general R. And again, I can play the same game. Each one of these things are twisted ideal sheets of points, N1, N2, all the way to R, and divisors 1, divisor 2, divisor all the way to divisor R. And of course, I can look at the difference of divisors at each level, and for R many vertices in here, I can have R minus 1 many detected curve classes. So this is our definition of the nested inverse scheme. For any R bigger than equal to 1 sequence of non-negative integers, and R minus 1 sequence of detected curve classes on the cohomology, second cohomology of the surface, the nested inverse scheme is fitting as a closed subscheme in the ambient product of inverse. So what does this mean? You have R many integers and R minus 1 many curve classes, so the last piece doesn't see any curve class in R. Now I hope that with all of this notation and these pictures, it's obvious to you why I have one curve class better than the number of non-negative integers. But these are seeing the difference of these divisor classes. Okay, and this guy transcribes this is basically what I just said. So transcribes is two-folds of zero-dimensional subschemes, which are elements of this product of inverse points for N1 when R, and R minus 1 two-folds of effective curve classes for elements of F theta 1 to F theta R minus. Such that the maps, which I just told you how I obtain, are injected. So this is the algebraic way of constructing a nested inverse scheme for any R. Okay, so what is it we are trying to do? We are trying to understand, in order to geometry of these moduli spaces, we are trying to calculate invariance of these moduli spaces. What does that mean? Of course, the virtual fundamental class, I need to tell you what it is, even though I know everyone here is correct than me. So, let's say for manifold, for example, n-dimensional manifold, in general, we know that invariance of that manifold is given by integrating the cohomology class against the fundamental class of that manifold. And that cohomology class needs to have a degree in cohomology with the degree in the homology of the manifold, which is the degree of the fundamental cycle, so this is H2M, if the manifold is n-dimensional. So for example, well, the characteristic of the manifold can be written as the integral of the substrate class of tangent cycle within the fundamental class. If your space is not a manifold, such as my moduli space, nested inverse scheme, it could be singular, it could be given somehow, it has multiple components, not equidimensional, it could have the property that is not expected dimension even. Then the procedure is to construct some cycle in the child group, the homology if you like, of your space, it's a graded group, graded string, and inside here you construct a cycle which sits inside the graded piece, which such that the degree is exactly the virtual dimension of your space. So this is a cycle which represents your space as if it's sat in correct expected dimension. And this is called the virtual fundamental cycle, and the invariants of the space are given by integrating the appropriate cohomology classes against the virtual fundamental cycle. Okay? So this is what you're trying to do. So this is our theorem. if S is a non-singular projective surface over complex numbers, and on the basis of the canonical bundle, the Hilbert scheme for some r bigger than equal to 2, 2 plus integers, and r minus 1 sequence of effective curve classes, this is space we can construct a virtual cycle for, and this is that virtual cycle. It sits inside some degree of the homology of the Hilbert scheme, and this is the formula for the effective dimension of the Hilbert scheme. You can use Grothendieck rough theorem to calculate this formula. Now, if there is no curve class, of course you can have nesting of points inside each other, then this whole sum goes away. You see, this depends on data I. So, let me just write this one in here, because this is kind of itself important. If there is no curve class, so the data is equal to 0. So this is the virtual cycle, and, well, it's constructed as a virtual cycle, we need some objects, we understand the information and instructions that I will talk about. Okay, so one of the things we can do is to simplify the problem and look at only n equals the twofold densing. This is the example in my picture. We need n1, n2, and one curve class for understanding the twofold densing of one effective flexing of an algebraic surface inside surface. So this is the theorem that he proved. The virtual fundamental class in this case recovers some of the known theories. So the object actually depends on n1, n2, and data. So if you set them equal to 0, it in some sense if you turn them all, and you can recover some of the known theories from the past. For example, you can prove that if the curve class is equal to beta, and n1 is equal to n2 equal to n, well, what is this moduli state? This is the moduli state. If n1 is equal to n2, beta is equal to 0, your map C is from ideal shape of bunch of points to ideal shape of bunch of points, and this is identity. And so it's just Hilbert scheme of points, and if you look at my formula for the virtual effective dimension, it's 2n. So here you can see that the Hilbert scheme of points that I mentioned earlier is 2n dimensional, fundamental cycle sits in 2n degree of the topology, and the virtual fundamental cycle also matches with fundamental cycle. So you're happy to see this. Now if beta is equal to 0, and n2 is equal to 0, okay. If that's the case, if beta is equal to 0, n2 is equal to 0, so this is space satisfied that n1 is not equal to 0. So some ideal shape of n1 many points, n1 some points, goes to ideal shape of no points. So what's the ideal shape of no points on the surface? Is the shape of holomorphic functions. We call it O, or destructive sheet. So this is that, but every ideal shape of course injected inside O. So of course intuitively it can be seen that the next Hilbert scheme again is the Hilbert of points on that surface. However, this is important because if you look at my formula, n2 is equal to 0 now, and the virtual dimension of the moduli space is half the dimension of the actual space. And this is one of those examples where you could have a smooth space and you put different instruction theories on it, and the virtual dimension and the virtual fundamental class depends on the instruction space, not instruction theory. So you can see in here that virtual cycle is not the fundamental cycle, it sits in half that degree. And okay, so this 2n homology class, 2n dimensional homology class capped with some n cohomology class, and that's some topological vector bundle of rank n1 you can get. Okay, so if you put beta equal to 0, and n1 and n2 are not equal to each other by different by 1. So you are looking at nesting of points inside on this algebraic surface such that the number of points is different by 1. So this is the only example of nested Hilbert scheme of points which existed before our work. And this space is smooth actually. And its invariance as well as its virtual fundamental class were studied by Manfred Lenz, whose picture I showed, and in the paper on topological sheets over Hilbert scheme of points in 1999. And our nested Hilbert scheme of obstruction theory and virtual fundamental class precisely captures his class. You see, the reason I'm mentioning these things is because it's not obvious that our virtual class matches it. So this is actually good luck, because I could have chosen different obstruction theory and virtual class of mine to be different from it. Both of them are correct, but you were happy to see that this is the case as well. And so our invariants are exactly invariants that calculate. If you put both of the points equal to 0, so no points, but this is just an ideal sheet of curves. In that case, the Hilbert scheme becomes Hilbert scheme of divisors, and you can see that the virtual fundamental class coincides with the virtual cycle constructed by these three people, Georg, Kavanagh, and Okudek. And they calculated the invariance against this class, and they call them Poincare invariants. So our virtual theory recovers Poincare invariants too. Okay? And finally, if n1 is equal to 0, and data is not equal to 0, so I1 was supposed to go to I2 twisted by some curve class, I1 is the ideal shape of no points. So this whole, and that's it. So this one is ideal shape of n2 many points twisted by some line bundle. If this part wasn't there, if n2 was equal to 0, if you look at this section, 0 locus of this section gives you the divisor C, and that's the natural Hilbert scheme of divisor on that. The parameterizing is just natural Hilbert scheme of divisor on that surface. However, because now you can see that your functions are having normorphic poles along the curve, but then they vanish at line of points, the picture that you need to have in mind about this is your space is parameterizing divisors with points on them. So for every fixed curve class, your space is Hilbert scheme of points on that curve. And as you vary the curve, okay, so there is a Hilbert scheme of curve that has a universal family, if you like, and as you vary the curve for every single element of that Hilbert scheme of curve, you get a Hilbert scheme of points on those. So this is something which is a relative Hilbert scheme of points on some universal curve given by the Hilbert scheme of curve. And this is was studied by Poincare and Thomas in the context of their stable pair theory on surfaces, and the virtual class were constructed later by Kuhl and Thomas using the stable pair theory of Poincare and Thomas on surfaces. And again, we were happy to see that if you should specialize our virtual class to this information, we cover their invariants. And we also recovered the reduced stable pair variance of Kuhl and Thomas. So the next Hilbert scheme is interesting because not only is some new objects and well-defined, it also recovers and glues some of the known invariants and some of the known theories from the past. Okay. Now let's call these invariants n. So this is the nested invariant, and I'm still in the case that I have twofold nesting. I have n1 and some curve class, and this is that appropriate cohomology class D1. Don't ask me why I call it D1. Just because I stole it from my neighbor. So some cohomology class integrated against this virtual cycle, the virtual dimension I gave you, is giving us invariants. Okay. So I talked about construction of these spaces and the virtual cycles and so on, definition of invariants. Now we would like to compute them and hopefully calculate numbers and see if there are any connections between these things and other parts of, some triple geometries or maybe even physics. So for each of the calculations, I will again have theta equal to 0. So this is the nested Hilbert scheme of points, but the number of points could have large gaps between them. Not just one. So this is highly singular, and it has a virtual cycle. And the virtual dimension is n1 plus n2. Okay? Alright, so this is the nested Hilbert scheme of points, and my notation is f of n1 bigger than n2, and why is that? Because if you want I1 sits inside I2, and these are functions vanishing on n1 many more than n2, and equal to n1 should be bigger than n2. Okay, so as I mentioned, the nested Hilbert scheme sits inside the ambient product of Hilbert scheme. So this is sub T inside here, and the reason that this simplifies the calculations is that these ambient guys are removed, like what I showed you before. Okay, so you would ideally like to integrate some homology class alpha prime or something of appropriate degree, I call it T1, to get the virtual cycle in here. And then we were wondering if you could use the